As early as 1978, Jarrow and Dudnick wrote a paper presenting a methodology to solve the problem of designing subsystems, HVAC, subjected to uncertain demands. Uncertainty in weather prediction under changing climate, and uncertain weather data information due to the use of synthetic weather data files. 1. Use of synthetic years that do not represent a real year, and 2. Use of a synthetic year that has not been generated from recorded data in the exact location of the project but in the closest weather station. Differences between the design and the real building: conductivity of thermal bridges, conductivity of insulation, value of infiltration or U values of walls and windows. Doors and windows opening, use of appliances, occupancy patterns, or cooking habits. The type 1 from this grouping have been divided here into two main groups, one concerning the uncertainty due to climate change, and the other concerning uncertainties due to the use of synthetic weather data files. Concerning the uncertainties due to climate change, buildings have long lifespans. For example, in England and Wales, around 40% of the office blocks existing in 2004 were built before 1940, 30% if considered by floor area, and 38.9% of English dwellings in 2007 were built before 1944. This long lifespan makes buildings likely to operate with climates that might change due to global warming. De Wilde and Coley showed how important it is to design buildings that take into consideration climate change and that are able to perform well in future weathers. Concerning the uncertainties due to the use of synthetic weather data files, Wang et al. Showed the impact that uncertainties in weather data, among others, may cause in energy demand calculations. These deviations on the demand were smaller than the ones due to operational parameters. The conclusion of this paper is that occupants will have a larger impact in energy calculations than the variability between synthetically generated weather data files. The spatial resolution of weather data files was the concern covered by Eames et al. Eames showed how a low spatial resolution of weather data files can be the cause of disparities of up to 40% in the heating demand. The reason is that this uncertainty is not understood as an aleatory parameter but as an epistemic uncertainty that can be solved with the appropriate improvement of the data resources or with specific weather data acquisition for each project. In the work of Peterson, uncertainties of Group 2, workmanship and quality of elements, and Group 3, behavior, of the previous grouping were considered. Peterson showed that the total energy use follows a normal distribution with a standard deviation of around 7.6% when the uncertainties due to occupants are considered, and of around 4.0% when considering those generated by the properties of the building elements. The results of this project show a significant gap between the energy used expected before construction and the actual energy use once the house is occupied. The authors emphasize the importance of thermal bridges that were not considered for the calculations, and how those originated by the internal partitions that separate dwellings have the largest impact on the final energy use. The dwellings that were monitored in use in this study show a large difference between the real energy use and that estimated using SAP, with one of them giving 176% of the expected value when in use. Hopfe has published several papers concerning uncertainties in building design. A more recent publication at the time of writing looks into uncertainties of Group 2 and 3. The random parameters are sampled to generate 200 tests that are sent to the simulator, VA114, the results from which will be analyzed to check the uncertainties with the largest impact on the energy calculations. This work showed that the uncertainty in the value used for infiltration is the factor that is likely to have the largest influence on cooling and heating demands. Another study performed by De Wilde and Wei Tian compared the impact of most of the uncertainties affecting building energy calculations taking into account climate change. De Wilde and Tian used a two-dimensional Monte Carlo analysis to generate a database obtained with 7,280 runs of a building simulator. A sensitivity analysis was applied to this database to obtain the most significant factors on the variability of the energy demand calculations. Standardized regression coefficients and standardized rank regression coefficients were used to compare the impacts of the uncertainties. Their paper compares many of the uncertainties with a good-sized database, providing a realistic comparison for the scope of the sampling of the uncertainties. The work of Schneiders and Hermelink showed a substantial variability in the energy demands of low-energy buildings designed under the same specification, passive AOS. Blight and Coley, Blight, 2012, showed that variability can be occasioned due to variance in occupant behavior. It should be noted that the use of windows and doors was included in this work. The method was developed using the Time Use Survey, TUS, of the United Kingdom as a reference of real behavior of occupants. This database was elaborated after recording the activity of more than 6,000 occupants in 24 hours diaries with a 10 minutes resolution.